Okay, so it's 2:02. Let's get started. So hello everyone, welcome to Ask Seminar series. I'm John, the seminar coordinator, and I will be moderating the seminar with Kathy, our communication manager. So some housekeeping. This seminar is being recorded, and we will post the recording on our YouTube channel. And after the presentation, we'll have the Q&A session. Please feel free to bring up any questions you may have, and we encourage you to speak up. If you don't have a mic, you can chat other questions. I think that's pretty much what I have. I'm going to hand the ball over to Kathy to introduce the speaker. So Kathy, please go ahead.
Thanks, John. So I'm excited to introduce our speaker today, Sean Peters. Sean Peters is an assistant professor in the Department of Aerospace Engineering Sciences at the University of Colorado Boulder. His research advances low-resource radar remote sensing technologies for monitoring terrestrial, planetary, and space environments. His core research agenda centers on developing passive radar systems and signal processing techniques that leverage ambient electromagnetic emissions, natural radio-astronomical, and anthropogenic to observe extreme environments such as ice sheets, ice shelves, and icy moons. Before joining CU Boulder, he was an assistant professor in the Department of Physics and a Space Systems academic group, a faculty affiliate at the Naval Postgraduate School in Monterey, California. So I'm just going to go ahead and hand it off to Sean Peters. So thank you.
Thank you, Kazi, for the introduction. Thank you for the invitation to speak today, and thank you all for being here. I would like to start my talk by just saying it's going to be split into two halves. So the first half, focusing on how we can use the sun as a radio signal to monitor glaciers. I'll show some field testings from example from here when I was at Store Glacier, Greenland. And the second half, I'll connect it to more of the recent work that my group is doing. So to get started, when we're thinking about traditional radar systems, we think about radars that transmit these signals into the glacier and receive the reflections coming from the bed. But I'm going to talk about a different type of radar today that exploits ambient radio signals coming from the sun and from Jupiter. And so as a radar engineer and instrument scientist, I'm interested in how we can make lower resource radar systems that could help us when we're trying to connect and collect these measurements over larger scales and larger time periods. So just some background, like as you mentioned, I've been doing this work since my Stanford PhD program, where I went to Greenland to test this at Store Glacier. So I mentioned how we've traditionally thought about radar systems. And when we think about radar remote sensing, there's a lot of observations that we can make, starting from sea ice observations, thinking about our atmosphere and aerosols, thinking about the space environment, or looking at the biosphere and looking at tree water content and soil moisture. But today, I'm going to focus on how we can use radar remote sensing to monitor the cryosphere, all of our glaciers, ice sheets, and ice shelves. And the fundamental question for why we're developing these types of radar systems is because advancing technologies that can observe the processes, conditions, and physics that govern ice sheet behavior is critical to projecting their sea level rise contributions. If we look out to the year 2100 and beyond, what we notice is that there's a large range of uncertainty when it comes to predicting sea level rise. Two of the main questions are how much sea level rise and how fast is it going to be occurring. So we can get more observations of critical processes such as ice thickness measurements or better understanding ice sheet behavior. We can help constrain those sea level rise predictions. Now, the principal tool that glaciologists currently use right now to study ice sheets and ice shelves is what's known as airborne radar sounding. So airborne radar sounding can transmit a pulse and receive a reflection coming off of the surface and the subsurface in order to monitor conditions that are happening beneath polar ice sheets. And so if we look at a map of the Antarctica radar profile coverage on the right, where you see are the blue flight lines where we're able to capture these observations of the ice shelf. But one of the things that we notice for these profile coverages is that it happens, let's say, seasonally at best. Now, for these airborne radar sounding measurements, as I mentioned, we're transmitting a signal, we're measuring the reflections coming off of the surface, the internal layers, and the bed of the ice sheet. We're capturing this received signal, and we start aligning these signals into range profiles known as a radargram, which gives us an idea of the surface reflection, internal layer structures, as well as the bed of the ice sheet. And so it can give us an idea of the evolving conditions of the internal structure of the ice sheet, as well as the material or the reflective properties coming from the bed of the ice sheet. Now, as I mentioned, right, we have this extensive spatial coverage on the Antarctica and Greenland ice sheet. But what I'd like you to keep in mind is that this is limited temporally to a single snapshot in time. These flight lines often don't get repeated, or at best, they're repeated at a seasonal case. But they're very useful because we can use this Antarctica radar profile to coverage to get an idea of the map of Antarctica's subsurface, which again is very important when thinking about projecting sea level rise. Now, on the other side, we can use stationary ground-based radar systems. These radar systems are great in the sense that they give us these continuous observations. So, for example, the internal layers that can vary on the order of days or hours, or the changing bed conditions of the glacier that, again, can be a process that is much faster occurring than the whole seasonal airborne radar flight lines. So we can get better measurements in terms of a temporal resolution for the internal layers and glacial water storage and ice sheet bed thickness measurements. The other thing we can do with these ground-based radio echo sounders is we can provide temporal measurements of things like basal melt rates and glacial water storage and vertical velocities, again, to give us an idea of the involving conditions within our cryospheric subsurface. So a really powerful tool on how we can measure the temporally varying subsurface, which is important, again, when we go back to the idea of trying to project sea level rise. Now, one challenge with these stationary ground-based radar systems is that they're at a single location, and of course, they're exposed to these extreme conditions. The example left is an example of a MIMO-based array that we set up on the surface of Store Glacier, Greenland. But we came back a year later, and unfortunately, a crevasse had opened up underneath our radar system. So, of course, it could be a challenge to try to deploy these systems for a very long time. And this is also a very expensive system. So you can imagine if you try to have stationary ground-based radars covering a large region, that'd be very expensive to do. And given the extreme conditions, if you were to lose one of these sensors, it could be a very valuable loss. So the idea is perhaps we could develop a more low resource system that's also lower cost that we could deploy at a very large scale to satisfy the stationary ground-based radar system measurements as well. So that's the two sides that we have, the need for both spatial and temporal coverage. On the left, we have the airborne radar sounders that can provide that extensive spatial coverage, but are limited temporally to a snapshot in time. And on the right, we have our ground-based radar systems that can provide more of those continuous temporally fine observations, but can only do so at a single location. And in both cases, these existing radar systems are fundamentally limited by the need to transmit their powerful signal in terms of cost, power, size, and logistics in order to perform that continuous long-term monitoring at the ice sheet shale. So that's the idea behind one of the first main projects that I'm going to talk about today, which is the passive approach to monitoring glaciers. The idea is that we're trying to develop a low resource passive radar that can eliminate the need to transmit the signal, and instead receive ambient radio signals such as the sun or Jupiter or anthropogenic sources in order to provide those temporal and spatial observations of ice sheets, ice shelves, and glaciers. The idea is that we're receiving a direct path that's going to be serving as our reference signal, and we're going to receive a path that propagates into the ice sheet, reflects off the bed, and is received some delay time later. Then by using an autocorrelation-based technique, we can extract that direct path signal as well as the reflected path. And we can get two observations from this. One, the relative delay time between the direct signal and the sun echo gives us an idea that could map to an ice thickness measurement. And the second thing we can look at is the relative amplitude between the direct signal and the sun echo, which can give us an idea of the total attenuation, the total reflection losses, the scattering losses that occurred within the ice sheet. Now, this works because effectively within our band that we're receiving with, the sun is acting like a white noise source. And white noise can only match when itself when it's performing an autocorrelation. So we get these really sharp peaks that we're seeing for both the direct signal and the sun signal. So keep this measurement in mind as I go through the rest of the talk. The idea is we're going to start actually with a sea-cliff experiment in order to validate the measurement in the simplest case. We're then going to move to a Death Valley floor, which is more rough and more analogous to the bed of an ice sheet. It'll also give us a way to look at changes in phase and changes in measurements over time. The ice sheet measurement, I'll show our initial testing and field testing from Store Glacier, Greenland, in order to measure the ice thickness using the sun as a signal. And then finally, the implications for planetary, where oftentimes with these radar missions, the move towards lower resource, lower size, weight, and power requirements could be a beneficial use case for the passive radar technique that I'm describing today. And in each case, remember that the passive autocorrelation-based technique is looking to extract the amplitude and the delay time of the sun's echo or the ambient radio source that I'm describing. So starting with why we even thought this was possible, if you go back to the historical sea cliff interferometer experiment done by a group of radio astronomers in the 1940s and 1950s, what they observed is an interference pattern of the sun's power and other star patterns as its angle changed through the entire day. So in other words, it's receiving that same direct path, the reflected path off of a sea surface. And what they observed was an interference pattern of the sun's power as it rised and ebbed depending on the fringes and the number of fringes related to that interference pattern. They could then relate this to the height of the cliff or the position of the radio-astronomical source. But we're interested in a measurement that doesn't take tens of minutes. We're interested in a measurement that can happen on the order of microseconds. And so what we can do is take that same recording and take an autocorrelation of it to measure the direct signal as well as the sun echo, and then take that delay time between the two in order to map it to height of the cliff. Or you can imagine this as the perfect case of an ice sheet where it'd be trying to measure the ice thickness in this example. So with this in mind, we're trying to capture that peak in the autocorrelation. But there were a few challenges along the way. And to save us time, I just wanted to highlight two approaches. One of them being the fact that if you were to take a radio receiver and sit it on the side of a cliff, you'd find that's a very noisy environment. It has full of radio frequency interference. So we had to do removal of the radio frequency interference in frequency domain. In other words, we had to filter out the unwanted signals so that we could capture our sun signal. The second is what's known as spectral stitching. And the idea, and this goes back to radar systems and radar engineering, is that if you have a wider effective bandwidth or a wider spectrum that you're capturing, you can improve the resolution, you can improve the measurement quality. So the idea is we found a way to increase our effective bandwidth, similar to what step frequency radar does by stepping through adjacent bands, combining one large effective bandwidth, and then improving your range resolution that way before we get our final autocorrelation signal. So those were two really key steps in order to making this work. Now, we first tested this in a lab setting. So the idea is that we transmitted and received a modeled white noise echo file that we transmitted through the USRP, the software-defined radio that we're using, transmitted, attenuated down to the power level of what we expected for the sun, then amplified it using our receiver chain, and then received it. Then we autocorrelated that loopback file in order to show that we could indeed use our system in order to detect a really small echo peak in the autocorrelation that matches what we expected based off the delay time. So with this in hand, we then went back to the sea cliff experiment and we demonstrated that we could use this autocorrelation approach, again, receiving the direct path as well as the reflected path off the ocean in order to extract an echo peak delay time that matches what we expect of roughly 82.9 or 84 meters based off of the Google Earth estimate. So we were able to show that this worked in the sea cliff experiment. With that, we were ready to go to Death Valley to show that this could work off of a rougher desert floor, which is more analogous to the bed of an ice sheet. So the idea is very similar. We're going to set up our receiver on the side of a Death Valley cliff. We're going to measure the direct path from the sun, as well as the reflected path off of the Badwater Basin that we're observing from the Death Valley cliff. The idea in this case is that it's going to be a rougher surface echo. So we actually, even though it's really sharp here, it's a rougher surface echo. So it's giving us, some spreading as well as some decrease in the relative power that we looked at before. We used a different instrument that had a much longer integration time that also had better amplification in order to extract this echo peak from this Death Valley autocorrelation measurement. But again, we found that the peak matched really well with our expected delay time, where the two red lines are showing any uncertainty based off the estimated sun's elevation angle, the height of the cliff, which we used Google Earth to validate, and the local slope of the Death Valley floor. The other thing that we could do is because we have some stationary receiver and we're looking at a moving sun reflection point, we're seeing how the sun can change its reflection point over the time of day. And as it's changing over different regions of the Death Valley surface, it can perhaps have different reflected values, different autocorrelation measurements in terms of reflected echo intensities that we're getting back. So we're taking advantage of the sun's moving reflection point off the rougher desert floor. Just as two examples of how we're showing detected changes in range of the sun's echoes. So at the same test site, showing how the echo peak is located roughly at 3.3 microseconds, and then at a different time it was located at 5.9 microseconds, both of them within the range of uncertainty based off the sun's elevation angle, the height of the cliff, and the local slope of the Death Valley floor. As I mentioned, one of our goals was to show that we could detect changes in the reflectivity of the sun's echo. So for example, on the left, imagine this being as a radargram almost, where this is showing the fast time direction or pointing in the direction of the range. And then here, this range line is showing you the number of measurements that we collected. And what we're observing is the change in the reflected power over some period of time. So for example, showing the echo peak power in blue, and how as it starts going over different parts of the desert floor, that we're getting an increase in the echo peak power relative to this background noise. And this makes sense because when we think about our received power, it really is the convolution of our signal with the ground terrain that we're measuring with. So that gives us an idea of how we can measure changes in reflectivity of the sun's echo. And then third and most important is that we can actually detect changes in phase of the sun's echo. So if we were to look at the sun's velocity at that point, it's actually a moving sun signal, which makes sense as it's going over the Death Valley floor. But what we can do is look at changes in phase of the autocorrelation echo peak. And this goes back to those really fine phase measurements that can be done with systems such as APRES, those original measurements I was showing you related to basal melt rates and vertical velocities. They're taking advantage of the phase of the autocorrelation measurement or the phase of the radar measurement. So we were trying to show that we could do this as well. This phase is also important when we get to the idea of synthetic aperture radar because it enables that process. And so it requires that we can actually measure the phase, which we're showing matches really well with what we expect. So with that in hand, we were ready to go to an ice sheet to show our field testing at Store Glacier in order to measure ice thickness using the sun as a signal. Now, as an idea, we are setting up on Store Glacier. We have our instrument where it's going to have these bow tie antennas. Here's just an example of getting ready at the field site, setting up our system, getting ready to go. For our passive measurement, we of course would want to do this away from the campsite. That way we're away from any radio frequency interference from our campsite. But what we're trying to do is measure the sun's direct path, as well as the path that propagates into the ice, reflects off the bed, and is received some delay time later. Then using that same autocorrelation measurement, we're able to extract an echo peak delay time that matches really well with what we validated with two different techniques, one, a Greenland ice sheet model, and then two active radar measurement surveys near the test site showed by the range within the red line. So we're measuring ice thickness measurement of close to 1,000 meters using this approach. Now, we did some additional system checks in example, looking at the statistics of the received signal. As I mentioned, we expect our sun signal to be white noise. So we looked at the histograms of the received signal, showing how it matches these Gaussian white noise characteristics, as well as how the power spectral density of the histogram matches this exponential distribution, which is what we expect for white noise. And then secondly, looking at modeling the power spectral density of the voltages from the sun signal, from the galactic background noise, from our system voltage, in order to determine how much total integration time we needed in order to capture that sun signal. So we use 8 seconds of integration time for these different measurements. And then, as I mentioned, RFI filtering, the radio frequency interference removal, was a really key process in order to make this work. So the idea is that if you look at the top measurement, this is our measurement before removing any radio frequency interference. But then after you remove radio frequency interference by using a spectrum thresholding approach, it effectively flags and filters out unwanted RFI, leaving you with the echo peak that corresponds to the delay time that matches what we expect based off the sun's direct path and the reflected path. So we're doing two things. We're removing any unwanted radio frequency interference, and we're also improving the signal and noise ratio of our measurement, getting an idea of that ice thickness measurement for the Greenland experiment. The other thing that I haven't shown and wanted to talk about is the idea that we can improve our coherence of the sun's measurement by using what's known as coherent summation. And this goes back to the importance of the phase of the signal. So in other words, if we have multiple files and we stack them together or we coherently average them, in other words, we average them both in the real part and the imaginary part, we can improve the signal and noise ratio relative to just a single measurement. So in other words, we get a really nice signal and noise ratio after we perform coherent summation of the autocorrelations. So now that we showed this was possible, one of the key questions going forward was, what is the extent of passive sounding spatial and temporal coverage? When we think about the Greenland ice sheet, when we think about Antarctica, where could this technique be applied? Where it could be useful with sufficient signal and noise ratio? And at what times of the year? In order to do that, what we would do is project the passive sounding performance. So in other words, we look at our signal and noise ratio, we model what we expect in terms of the total attenuation, reflection, transmission losses. We take advantage of our integration time, which can increase our signal noise ratio. And then we can estimate our signal and noise ratio for different test sites as a function of the time of day so that we know and expect particular times of the day when this measurement will work. Obviously, it won't work when the sun is below the horizon. So just as an example of how we can use the sun to monitor Greenland's subsurface, I'm showing Greenland signal noise ratio in color for 3 different times of the year. So the summer, which makes sense that we'd have a greater signal noise ratio in the summer because the sun is available for more time of the day, the Greenland equinox, and then the Greenland winter. When it also makes sense in winter that certain parts of the Greenland ice sheet are no longer available to be measured because the sun is now below the horizon. Now, in each of these different cases, we typically want signal noise ratio greater than 10 dB so that we can say something about the rate of reflection that we get back. But what we're finding is that there's certain regions within Greenland where we can achieve really high signal noise ratio, which would be really great for this measurement. We also did the same thing, modeling our sun signal for monitoring Antarctica's subsurface. So on the left is showing the Antarctica SNR map for the summer, and on the right is showing the SNR map for the equinox. And what you notice in both cases is that the signal and noise ratio on the ice shelves themselves is much greater, which makes sense because of that ice-water boundary. So we're getting a really strong reflection back, meaning that we can have a high signal noise ratio measurement in both of those parts. Now, another thing to notice is as we start going to later times in the year, or in other words, when the sun starts to go below the horizon for more parts of the day, more of the ice sheet becomes off the table, but we can still start to measure those ice shelves, which is, again, really important when we're thinking about contributions to sea level rise and making sure that we can monitor these with sufficient temporal coverage. So that's a summary of how passive radar sounding can be used as a cost-effective continuous monitoring tool at the ice sheet scale. The idea, again, was we're simply sitting on the surface of the ice sheet, receiving an ambient radio signal, the direct path as well as a reflected path, and getting us an idea of where we can measure this on both Greenland and Antarctica, showing that this could be a valuable tool for several months of the year, which would be really great. Now, for the second part of my talk, I want to talk about the implications of the planetary aspect for this approach. So the idea is we're going to look at the design and analysis of a passive HF radar that can use Jupiter's radio missions for different mission concepts, such as Europa Clipper. But we'll bring this back to how we've done some testing on Earth in order to show that this could work. But just as a brief context for this, I want to mention how passive radar sounding could use Jupiter's radio missions. So for example, if we think about the Europa Clipper mission and the radar for Europa assessment and sounding ocean to near surface, it has an HF channel and a VHF channel, very similar to the sounders that I've talked about on Earth. So the HF channel 9 megahertz is looking to probe deep into the icy shell. The VHF 60 megahertz looking at the more near surface features such as chaos terrain. The idea is that we're trying to get an idea of the ice shell thickness, as well as the internal structure and chemistry measurement. So when we're thinking about this, we can provide really valuable observations of Europa's icy shell. But there is one challenge with the HF radar that I want to mention, and it's that Jupiter's radio missions, you can effectively think of this as a really high-powered jammer, a powerful ambient noise source within the HF band. Effectively, particles from the Ioplasma torus interact with Jupiter's magnetosphere and create these decametric bursts that you're seeing here, that happen to be in the same frequency band as the HF system on the recent instrument. And because they're in the same system, and because they're 5 orders of magnitude greater than the galactic background noise, what we find is that it can serve as an interfering source for the HF system. So in other words, instead of this classic active sounding case where it's noise-free and we're able to clearly see the surface features, if Jupiter was on and had one of these decametric bursts blasting, you're no longer able to recover that scientific measurement that's really valuable to obtain. So the idea is, instead of fighting Jupiter's radio emissions, what if we use Jupiter's emissions as a source for passive sounding from Europa? So one of my collaborators, he looked at this idea of capturing Jupiter's direct path, as well as reflections that come off of the surface and the subsurface, and then using that autocorrelation-based technique in order to extract the altimetric measurement, as well as the ice depth measurement. So we want to simulate what this might look like. The idea is we're going to simulate a passive synthetic aperture radar approach for the Europa Clipper mission. We define some sensor geometry with a receiver flying in this direction with some incoming plane wave that corresponds to the Jovian radio burst that's receiving. Keep in mind this idea of the ridge that's flying over. So it's going to be flying over this flight track, flying over this ridge, and we're going to try to capture this surface topography that you're seeing here with a passive HF approach. In order to create this simulation, we really wanted to make sure that match the rhyme and reason instruments for the Europa Clipper mission. So we looked at modeling using the passive signal flux density, which what we expected for the Jovian burst, comparing it with active transmit power, the same center frequency at 9 megahertz, receiver bandwidth 1 megahertz, using a comparable integration time to an active trip length, and then also using this for the expected PRF and sensor velocity. Now, for this approach, we use a backward projection approach. Effectively, when this plane wave arrives and reflects off of these facets, we're going to delay in some of the facets so that we can contribute all their contributions coherently and then focus the result to the singular facet point. So looking at the results first for the active radar simulation, on the left is the range compressed image, on the right is the active SAR process image. Again, we're trying to capture that surface topography that I showed you on the previous track. And for this active SAR case, when no Jovian burst is occurring, we show that we can easily reconstruct this topography, which makes sense. Everything is working for the rhyme and reason instruments for the Europa mission. We want to compare this to the passive radar simulation. So on the left is the range compressed result using Jovian bursts as a source, and showing how we can still recover, even if it is lower signal noise ratio, we can recover that range compressed result, the surface topography, as well as the improvements that we can get in terms of azimuth resolution and signal noise ratio when we perform passive SAR processing. So showing that this can work to capture the surface of Europa and actually look at the topography in order to gain valuable scientific measurements when Jovian bursts are occurring. So now that we showed that this was possible for observing the surface, another key question we were interested in is, could we use this to characterize Europa's ionosphere? And the idea is that this passive HF radar that I've described can be used alongside an active VHF radar to serve as a low resource approach to correct for ionospheric dispersion and characterize the ionosphere of Europa. So ionospheric dispersion, when we think about it, it's going to create both a signal delay and pulse broadening, but we can correct for the signal delay and pulse broadening in order to improve the range measurements for altimetry purposes. So the idea is, again, for Europa's ionosphere, for both the HF and the VHF, it's going to produce this delay and pulse broadening. So on the left is the VHF result, so effectively a chirp that's been pulse compressed. This is our measurement for the charge-free result if there was no ionosphere. But if an ionosphere is present, it's showing how there's a delay, a shift, which can mess up your altimetric measurement, as well as some pulse broadening, which can reduce your signal and noise ratio. Similarly, for the passive HF echo peak, I'm showing the charge-free result as if no ionosphere was present, and then the implications if an ionosphere is present in terms of the decrease in signal noise ratio, the pulse broadening that I've described, as well as that delay time, which means it confuses the range measurement that you're trying to capture. So the idea is we can actually use this relative delay time between the two different bands, the active VHF in red, and then the passive VHF in the dashed line, in order to correct for this ionospheric dispersion. We can use this relative delay time in order to estimate that phase shift. That phase shift is related to the total electron content, and then we can correct for the Europa ionosphere, showing the corrected result in yellow, where now we've effectively removed that pulse broadening effect, and we've also removed that delay effect, and we've also at the same time gotten an estimate of the total electron content for Europa's ionosphere. So what we found is that we could perform these range error corrections as well as provide an estimate of the total electron content of Europa's ionosphere. And we found that for all realistic values of Europa's ionosphere, we could use this passive HF approach to estimate the TEC and correct for these VHF range errors for both altimetry and sounding purposes, showing how this could work over a wide range of total electron content and showing what was the required integration time for the passive HF receiver in order to make this work. And then showing how this could reduce the expected range error, which is, again, a sole purpose for trying to provide those really accurate altimetric measurements, trying to have range errors that are less than 3 meters in this example. So now that we've shown that we can estimate the total electron content and improve our altimetric measurements, the other idea is that because of the geometry given by the HF receiver, we can exploit this passive off-nadir geometry to create various pathways of Jupiter's radiant emissions and invert the latitudinal and vertical structure of the ionosphere during a given flyby for these wide range of incidence angles, showing how we can use this technique for wide range of incidence angles based off of changing ionospheric eccentricities or how homogeneous or heterogeneous the ionosphere looks like, showing that we can use a wide range of incidence angles to make this approach work for the passive HF radar. And just as an example, a student has recently shown how we can use this active passive dual frequency radar tomography reconstruction approach in order to look at characterizing Europa's ionosphere. So on the left is an enhanced ionosphere showing an anomaly that's related to, let's say, a plume, how we can use the active VHF and the passive VHF in order to reconstruct this ionosphere profile, taking advantage of the various slant angles that I described before, and showing how there's a really small difference between the true profile and what we measured by using this reconstruction, where again, the goal was to invert the latitude and vertical structure of the ionosphere during a given flyby, taking advantage of the wide range of incidence angles that can't be captured if you're only looking nadir with an HF or a VHF radar system. So that was an example of some of the previous work, but I want to really highlight now some of the work that my group is currently doing, looking at applications in radar signal processing, radar system design and testing, modeling these remote sensing capabilities for not just cryospheric measurements, but other planetary and space science measurements, and how we can apply this to other planetary mission concepts. So first, starting with some of the passive radar signal processing developments, because this will be really important when we think about how we could recycle anthropogenic sources. Think about the TV stations, the radio stations, the satellite signals that are available that could potentially be used as a signal source for passive radar sounding. Other examples looking at passive synthetic aperture imaging algorithms. I gave one example today, but others could explore looking at deep learning in order to implement passive synthetic aperture radar using these noise sources. And then finally, adaptive radar signal processing techniques where we can improve the signal noise ratio of our passive radar measurements, which can improve the depth sensitivity of that measurement, which would be really valuable for glaciologists. So one example I really want to highlight is how we could use anthropogenic sources, such as MUOS communication signals or TV signals, in order to use these as signals of opportunity for passive radar sounding of glaciers. As I mentioned, we can measure a direct path, as well as a path that propagates through the ice sheet, reflects off the beds, receives some delay time later, take an autocorrelation of that measurement in order to match the ice thickness measurement and relate this again to the glacier that we're looking at, relate to the geometry in order to map ice thickness. So this is an example for the DVB-T signal, effectively a TV signal, because it has some interesting spectrum characteristics. The quality that you're getting in terms of these side lobe behaviors is really interesting and something that's hard to characterize that we're still looking at. But the idea is that the main echo peak that we're looking at can serve as that delay time estimate, which we can map to an ice thickness measurement. Secondly, I mentioned satellite signals such as MUOS, how we can take autocorrelations of those signals and use that as an echo peak that we're receiving the direct path, the path that propagates into the ice, reflects off the bed, receives some delay time later, use that in order to determine an echo peak that can map again to an ice thickness measurement based off that geometry. So just two key pieces of how we can use human signals in order to create and recycle passive radar measurements. Another key idea that I want to emphasize is how we can implement what's known as direct signal suppression in order to improve the signal noise ratio and increase the depth sensitivity of the measurement. So in other words, we go back to the idea of receiving a direct path and a reflected path. We're trying to do this with a single channel. Because of that, the direct signal is so strong that effectively acts as a source of interference for our weak reflected path. So if we can use adaptive filtering, what we can find is that if we look at our autocorrelation before we apply direct signal suppression versus after we apply direct signal suppression, we can improve our signal noise ratio, which means we can improve the depth sensitivity of our autocorrelation echo peak, which again is great when we're trying to think about the extent of spatial coverage that is available when trying to implement passive sounding. The other part that I want to emphasize is how we can use this for passive radar system design and mission concepts. So thinking about miniaturizing this device, making it more system and ruggedized, where we can implement array-based passive sounders or look at ambient radio noise tomography with really long offsets, which can use cross correlations and massive correlations. And then finally, making this small enough and recognized in space weather, space ready, so that we can implement on CubeSats or small sats for passive radar sensing. Similar to what has been done with Sunrise and Cygnus, the hope is that we could do this for passive radars as well that use these signals of opportunity. As a couple of examples of passive systems and passive applications, I wanted to show how we could use passive radar sounding for fur and aquifer monitoring. Until now, I focused how we can measure the ice thickness bed, but I really want to emphasize here, we're looking at the near surface. So in other words, if we're looking at the expected depth of unsaturated firn and the water table level corresponding to some aquifer, we can use that same approach, receiving a reflected path as well as the direct path, and then measuring the time delay between the two. Given some temperature, saturation environment, some firn density structure, there's going to be some differences in delay time, and there's going to be some interesting reflections coming through each of the individual firn profiles. That's going to disrupt our measurement, but we can still extract some autocorrelation that shows an echo peak corresponding to that water table level. So the idea is we're going to try to see if we can monitor this water table level over several months of the year. And how does this passive radar measurement change when we think about the changes in temperature and saturation that can occur within these firn aquifers? So that was one of the things we looked at, modeling the system performance for passive radar sounding, looking at the signal noise ratio as a function of the water table depth, as a function of the saturation, and as a function of the temperature profile within the firn that we're measuring. Secondly, also observing how this change as a function of sun angle, because as I mentioned, the sun angle is going to be available for different times of the year, that maximum sun angle, that also has important implications on the signal noise ratio. So our simulations accounted for these varying sun angles over the wide range of plausible environmental parameters, such as the firn water table depth, saturation, and temperature and density. So with these two in hand, we want to estimate and simulate what this might look like with a firn temperature time series. So we actually used FA16.4 firn core density data, as well as FA15.1 firn temperature time series data, and simulated what a water table might look like, where there's some recharging event over the melt season, and then what it might look like if our radar was, say, buried over this snow accumulation over some period of time, to look at what a time series measurement might look like for these passive radar measurements. So in other words, going back to the idea of those radargrams and looking at the reflections, these reflections are corresponding to that water table level, showing what months we're actually able to capture the reflection. It makes sense that the reflection goes away in the winter months, right? Because the sun is below the horizon. But how it comes back really strong in the summer months, and also how we can see that area, that region, that time period where we have the recharging of the firn aquifer. So this was a great case of how we could simulate passive firn monitoring over an 18-month period to show how we could monitor the firn with really fine range resolution and temporal resolution. Okay, and then the last project that I want to mention is what's we like to call Panther, so the Passive Autonomy Navigation Topography Habitability Exploration Radar. The idea is that we want to use a dual frequency radar that takes advantage of the VHF signals from the sun, as well as the HF signals from Jupiter, in order to measure shallow sounding of the near subsurface, as well as the deeper sounding using the Jovian HF. So going back to the idea of having a really low resource instrument, we could have a low size, low cost, low weight instrument. We could actually deploy this on a drone and have this go to different locations, measure these shallow sounding measurements as well as deep sounding measurements, use this as a way to perform passive sounding of the subsurface, and then fly to the next destination. So we've done some initial field testing at Death Valley that we conducted last April. The objective to is demonstrate that we can measure reflections of the Jovian radio burst and the solar noise. One of the key ideas behind this is, again, we're operating a system using commercial antennas that are much shorter, these electrically short antennas, where traditionally, if you look at an active HF system, it requires the system be roughly 30 meters in length. Here we have a system that's on the order of 1 or 2 meters. So we have an idea of the test setup, right? We're trying to measure the direct path as well as reflection coming from our Death Valley terrain. So one of the things we want to look at is the Jovian burst test. So what we're looking at is the probability of these Jovian bursts occurring for the given test period. These Jovian bursts, we're looking at a probability map showing the region where we're recording. We want to record when these bursts were occurring. Here's showing the probability of the burst for 3 different times, where this will be the time, this red region, where we expect to have the highest probability of a burst occurring, and then showing the relative position of Jupiter for that time with respect to where it was in elevation and azimuth position, where it matched with what we were receiving within our recording window. So as an example, and one of the key results from this Panther experiment is that we performed receiving the power spectral density as well as the autocorrelation measurement. So the same idea of receiving the direct path and the reflected path. And what we notice is at this time, the red point, where again this maps to when we had the highest probability of the burst, we see an elevated power spectrum, which is what we'd expect for receiving a wideband HF Jovian burst signal. And then in the autocorrelation, what we notice is a really strong echo peak at the delay time that we were measuring at, which we were expect, which shows a high amplitude echo peak delay time at the time that we expect in terms of when the highest power Jovian burst was expected to be occurring. So this is one of the key results showing for the first time that we could potentially use Jovian burst as a signal source for passive radar measurements. And so I'd like to conclude my talk by just reminding everyone that, we started from theory, simulation, lab, and field testing to demonstrate that we could use passive sounding using the sun as a radio source to measure ice sheet thickness for the first time. But since then, we're looking at other ambient radio signals, Jupiter, and other anthropogenic signals that could also be used as a signal source for measuring ice sheets. If so, then passive radar sounding could enable this continuous and widespread monitoring of Antarctica's and Greenland's subsurface conditions, and could also potentially serve as a low resource tool in order to probe the icy moons of Jupiter. And so finally, my current research is currently focusing on providing this richer understanding of the technique by projecting this ambient noise, passive radar performance, and potential limitations when designing these future radar sounding missions. So with that, I'd like to thank all my collaborators, all the students who have worked with me on these projects. And again, thank you all for your time today. And I'm happy to answer any questions.
Thanks, Sean. So now if you have any questions, please raise your hand, or you can just type it in the chat or let me know that you have a question just so I know to cue you.
I have a question. This is a very impressive talk. Can you elaborate on how you beat down the noise and improve the signal-to-noise ratio by doing some the hardware and software manipulation thing? So I think there is like one slide about this, and I don't quite get it.
Yeah, a couple different ways. So I saved this more for an engineering slide where we're showing the hardware as well as the signal processing. So the idea is that there's can be various stages of filtering. The software-defined radio can listen for a long integration time, let's say 8 seconds. It can record over 15 megahertz bandwidth. We also use really low noise amplifiers, which is great when we're trying to have a lower noise floor. So a longer integration time can help improve your signal noise ratio. And the other thing that I mentioned is how we can use what's known as coherent summation in order to increase the effective signal noise ratio as well. So think of the noise averaging out, but the echo peak remaining after you perform this coherent summation. So several factors went into this, increasing the integration time, using really low noise amplifiers, and then also using coherent summation in order to improve our measurement signal noise ratio.
Okay, great. Then for a typical very good low noise amplifier, I wonder how much is it?
Yeah, 0.5 is really good. When you look at commercial low noise amplifiers, they can range anywhere from 3 dB to 8 dB. The typical ones within the software-defined radio receiver itself is normally around 8 dB noise figure. But if you can get these lower noise figures that have 0.5 dB and have them in front of that, the noise that you're getting is governed by the first low noise amplifier within your receiver chain.
I got you. Thanks.
Thanks. Do we have any other questions? All right. Well, if not, then we can give everyone back 15 minutes of their day. All right. Well, thank you everyone for coming. And big thank you to Dr. Sean Peters for giving us this great talk this afternoon.
Thank you all.
Great. Thank you. Have a good rest of your day, everyone.